So, acid bases and salts is our next unit. It's in chapter 19, and it will be the last unit of the semester for us. It's rather lengthy, there's lots of labs with it. Hopefully, you've been enjoying the video labs as much as I've been enjoying making them. I know it's not the same as being there, but it's the best we can do in this difficult situation. So, acid bases are super common substances. Um, there's lots of ways of talking about them. One of the ways is through descriptive chemistry. So we can describe various properties of acids and bases, and these are those properties. So, first of all, something you'd never do in the laboratory, acids taste sour. Things like lemon juice and vinegar are sour because they have acids in them. Lemon juice has citric acid, vinegar has acetic acid. Aspirin, old school headache remedy, has acetylsalicylic acid in it. Sour milk sours because lactose gets digested by bacteria in the milk and produces lactic acid. Okay, so lots of things. Anything that tastes sour probably tastes sour because it has some kind of acid in it. Now, if you get an acid on your finger and go like this, you're going to say, oh, it feels watery, unless you have a cut. I don't know if you've ever been cutting tomatoes or lemons or something like that, and you don't realize you have a cut until you get that lemon juice on your finger, and then it stings like crazy. But they're other than that, they feel watery. Um, Now, one of the original indicators was a substance called litmus that was derived from lichen, um, pigments in lichen. And if you have a blue piece of litmus paper, like down here, and you dip it in an acid like this, it turns red. So the rhyme that all chemists come up with is blue to red acid. To help you remember, red is the acid color. Now, a cool property of acids is that they dissolve many things like metals and carbonates and other minerals. So we've dissolved, this is magnesium strip in acid, and we've done that a number of times in this class. And then a key property of acids is that they neutralize bases and vice versa. Now, some common acids, these are ones you should already know by their formula and their name. So if you look at this, you should think HCl, hydrochloric acid, H2SO4 is sulfuric acid, HNO3 is nitric acid. These three are the big three laboratory acids, widely used in all kinds of different chemical processes. The king of chemicals is sulfuric acid. They call it that because it's the most common chemical in industry other than water. Super widely used in a ton of industrial processes. HC2H3O2 is acetic acid, which is the chemical name for vinegar, and then H2CO3 is carbonic acid, which is the chemical name for carbonation. Now, bases, their descriptive properties are that they taste bitter. Things like baker's chocolate. You may remember as a kid seeing your mom making brownies or something like that, and you saw the chocolate that she was using. You said, hey, can I have some? And then you taste it, and oh my gosh, it's super bitter. It's bitter because the cacao is an alkaloid. It's a plant toxin, and people tend to like bitter things. Um, Bases, if you get one on your hand, it feels slippery. So soaps and cleansers feel slippery because they have bases in them. The litmus color for bases is blue. So if you have a red piece of litmus like this and you put base on it, it turns blue. B for blue, B for base. And then the reason bases are good cleaners, is that they dissolve things like grease, lipids. They also dissolve proteins, so hair clogs and stuff like that. Okay, and it's also why soap dries out skin because the oils in our skin and the oils in cell membranes um, are dissolved by bases, and so our skin dries out. And then bases also neutralize acids. Some common bases, you should also know these by name and formula: NaOH, sodium hydroxide, old school name is lye or caustic soda, KOH, potassium hydroxide, NH4OH, ammonium hydroxide, household ammonia. CaOH2, calcium hydroxide, which is lime, not citrus fruit, but the white powder that they use to chalk baseball diamonds and stuff like that. They also use it in farm fields to raise the pH if you have acidic soil. And then MgOH2 is milk of magnesia, or magnesium hydroxide. Now, pardon me a moment, my computer's frozen. Okay, so those are descriptive properties. For a long time, we knew these descriptive properties, but we didn't know why. And in the late 1800s, a Swedish chemist by the name of Svante Arrhenius came up with a theory of why acids do what they do. So the active ingredient of acids are hydrogen ions. So when you have an acid in a water solution, it produces hydrogen ions, and those hydrogen ions, when they interact with your nerve impulses, your taste buds, it gives a sour taste. When it reacts with things like carbonates and whatnot, it dissolves them. Okay, so the active ingredient of acids are hydrogen ions. So here's how we make acids. We take hydrogen chloride, we bubble it in water, ending up with an aqueous hydrogen ion and an aqueous chloride ion. The generic version of this, HA, H for acid, or H showing it's an acid, and the A is the shorthand for acid, the negative ion in it. Okay, so you get a positive ion, the proton ion, and the negative ion. Okay, he went on to say that bases are substances in water solutions that provide hydroxide ions. So if you look back at all those common bases, they all had hydroxide in them. Okay, so the active ingredient in a base is hydroxide. Now, interestingly, when you add a hydrogen ion to a hydroxide ion, what would you get? You would get water. That's the essence of neutralization. Okay, now that worked for about 50 years, but then a Bronsted-Lowry theory came about to kind of broaden but also focus the theory of acids and bases. So Bronsted-Lowry theory says that acids are proton donors, which really doesn't change it that much, except it removes the idea of water solutions. So things can be acidic. Hydrogen chloride gas is not in water solution, but it still can donate a proton. So if you were walking around and there was a cloud of hydrogen chloride gas, it would do bad things to you. Those protons could do what acids do. Okay. And then the Bronsted-Lowry theory says that bases are proton acceptors. So here we have a hydrogen chloride gas reacting with ammonia gas, and the hydrogen chloride donates a proton to the ammonia, and then those two things react together to produce ammonium chloride. Now, if you notice, there's no hydroxide. So how could this be a base? Well, according to Arrhenius, it wouldn't be, but according to Bronsted-Lowry, it is, because it's a proton acceptor. So OH ions are great proton acceptors, but other things can also accept protons. Then the Lewis theory. Lewis was the guy that came up with the electron dot structure, and so he was all about electrons. And so he said that acids are electron acceptors and bases are electron donors, which is kind of makes sense if you think of acids being proton acceptors and protons are positive, then proton donors rather, and protons are positive, then bases or acids would be electron acceptors since they're negative. Now, some important terms that go with acids and bases. The first and most important is hydronium ion. A hydronium ion is a hydrogen ion in water, and when a hydrogen ion is in water, it will always bond to a water with a coordinate covalent bond, forming this hydronium ion. So consequently, when they give you the hydrogen ion concentration, it's going to be the same as the hydronium concentration. In fact, these two are used interchangeably. And then the third term that's used interchangeably is a proton. A hydrogen ion is a proton. So we can use hydrogen ion, proton ion, and hydronium ion all interchangeably. Okay. Polyprotic deals with the number of ionizable hydrogens, also called acidic hydrogen. So a monoprotic, mono means one, so it has a single ionizable hydrogen. Diprotic means two, so H2SO4 would have two ionizable hydrogens, and triprotic, tri means three, so phosphoric acid has three ionizable hydrogens. Amphoteric refers to a substance that can either be an acid or a base. Water is the classic amphoteric substances. It can donate protons, but it can also accept protons. And then another term that's important that we'll just touch on now, it'll make sense more when we talk about buffers, conjugate acids and conjugate bases. So when you take a weak acid and react it with a weak base, the weak acid will donate its proton to the weak base, forming what's called its conjugate acid. The base becomes the conjugate acid. And then since that what's left is able to accept a proton, it's called a conjugate base. So the weak acid forms its conjugate base. And that'll make more sense later. Okay, that'll do it for this introduction to acids and bases. The next section we'll talk about hydrogen ions and acidity, and basically we'll discuss the basis for the pH scale, which is something you're probably